Hello friends, welcome to Electronic Circuit Hub. So today we are going to understand about the simulation of zero crossing circuit, how you're gonna simulate or how you're gonna sense the zero crossing of your sine wave. So let us understand first the circuit flow and later I'll run the simulation and I'm gonna show you how you're gonna simulate this non-isolated zero crossing. If I say non-isolated zero crossing, what does it means? That if you look at here, this is my sine pulse. So the sine pulse I have given the amplitude of peak amplitude of 325 volt with the frequency of 50 hertz. And if you look at here, the ground of this signal, the sine signal is common everywhere. Okay, that's why I'm saying this is non-isolated zero crossing signal. You can able to sense this zero crossing when you have the non-isolated power supply, when you have your microcontroller is sitting at the same logic level, same level of your sine signal. Okay, let's say this is line and this is neutral, and your entire circuitry on the board has to sit on with reference to the neutral. Otherwise this circuit is not going to work. Okay, and this circuit I got from the book Art of Electronics, and this is completely for educational purpose. I haven't tested and built in the production, so this is going to be completely for educational purpose. And now let us understand the circuit flow. If you look at here, so this is my sine signal with the peak amplitude of 325 volt with the frequency of 50 hertz. Then I have the current limiting resistor, that is R7, and then we have the two diode D1 and D2. And basically this diode is connected, positive is connected to 5 volt and negative is connected to the same reference. So this is going to attenuate the clip your voltage higher than, let's say, 5.6 volt, and any voltage here less than 0.6 volt, the forward voltage of your D1 and D2. So the forward voltage of D1 plus 5 volt in this case, and in this case the minus 0.6, let's say the forward voltage of D2. And then we have R6 and R4. Again, R5, it's a pull up to the inverting terminal. At the end your input is connected to the inverting terminal. And then we have R2 and RT, which works as a Smith trigger to give the hysteresis to the output. And this is R3. In case of R3, what we have is, it is kind of open collector. I've connected this the 5 volt. So if I run the simulation straight away, so let's run the simulation and let's look at the waveform. And uh, view, zoom fit. If you look at the input, so this is going to be my input. The peak is 325, and after the 47 ohm, what you see here is we have very less voltage. The positive amplitude is around 5.6 volt and negative is 0.6 volt. Okay, because of the diode D1 and D2. Okay, now if you look at the voltage at this node, okay, anywhere at the input, even now because of the resistor divider kind of thing, your voltage further reduced down. Now the peak voltage is, in this case, is 2.1 volt, and here I can see is minus 0.26. Now this is for hysteresis. Let's look at the output. Okay, so your output is complete square wave pulse. And can you see the rise and fall time of this signal? Because of the operational amplifier, here I see the 0 volt and here the 5 volt complete pulse. And if you compare this pulse to your input signal, how it looks like. And since the amplitude of your second pulse is 5 volt only in compare with the 325 volt peak, so you see the less voltage. But what need to understand here is, whenever you have the zero crossing, whenever your sino signal is crossing the zero level, we see the logic change at the output of operational amplifier. The voltage, ec- the voltage of the voltage at output of operational amplifier is looks like in red, and exactly at the same time, whenever your sine signal is crossing the zero level, this is the zero level, it changes the logic. If I add this 2 in the plot pane, you will understand more. Now what I'm trying to make you understand here is 0 to 325, then again 0 and minus 325, and your signal at the output of operational amplifier is exact following the same. The signal is 0 and 5 volt. If you overlap each other, you will see here at every zero crossing, your logic level of op amp output is changing. Okay, your logic level of op amp output is changing at every zero crossing. Okay, so that is how you can simulate. It's a kind of non-isolated zero crossing signal, and with the help of operational amplifier, how you're gonna simulate, how you're gonna design the circuit for this. And this circuit I directly took from the art of electronics books. They have the multiple circuit. I tried to simulate, and then I thought of what is limitation of this circuit is. The limitation of this circuit is, the main disadvantage is it's a non-isolated kind of thing. We If you want to read the signal with your microcontroller input pin, then it's hard to read. If your microcontroller, you have the secondary separate low voltage ground, so it's hard to read it. So you have to think of making some kind of isolation between your AC high voltage signal and then your low voltage signal. But for now the circuit is non-isolated, and it perfectly, I can see here, it's perfectly working. Okay, so hope guys you understood how you're gonna simulate the zero crossing, how